Today we will talk about Layer 2 switching. I hope that after this session, you're able to understand Ethernet Layer 2 switching and how it differs from routing, understand MAC addresses and the MAC address table, as well as addressing and the position of a MAC address in an Ethernet data frame. Understand the virtual local area networks, VLANs, and trunks. Learn basic configurations of VLAN and trunk ports. First, let's look at the basics of Ethernet Layer 2 switching. On data network, routing and switching are very important. A switched network is the largest system on a conventional campus network. The network consists of 3 layers. Access switches work at Layer 2 to provide access services for users. A Layer 2 switch provides the following basic functions: allows terminal users to access networks, maintains the MAC address table and performs addressing based on MAC address, forwards and filters data frames, prevents Layer 2 loops and provides link redundancy. This is an Ethernet switch. An Ethernet Layer 2 switch only performs addressing and switching based on Layer 2 headers carried in data frames before forwarding the data frames. It does not concern itself with frame contents. For example, the Layer 3 header, which follows the frame header. When PC1 wants to communicate with PC2, it constructs a data frame, which includes a Layer 3 header. In this Layer 3 header, the source address is 192.168.1.1 and the destination IP address is 192.168.1.2. The source MAC SMAC address is PC1's MAC address 0050-5600-0001, and the destination MAC DMAC address is PC2's MAC address 0050-5600-0002. The switch forwards the data frame through a specified port. Such behavior is called switching. The data frame is unchanged before and after switching. Therefore, switching technology is said to use transparent transmission. The switch simply obtains the DMAC address from the Layer 2 frame header, searches the MAC address table for this address, and forwards the data frame to the entry mapped to the address. The Layer 2 MAC address is called a hardware address. MAC addresses are burned onto NICs of PCs and routers before they are delivered. In Layer 2 switching on an Ethernet network, a Layer 2 switch receives a data frame, analyzes the DMAC address in the frame header, and searches the MAC address table for a port mapped to the DMAC address. If a match is found, the switch forwards the frame through the corresponding port. If no match is found, the switch broadcasts the data frame. We will talk about this soon. A MAC address is 48 bits long and can be represented by 6 groups of 2 hexadecimal digits, 2 digits per binary octet. MAC addresses are classified into 3 types: unicast, multicast, and broadcast. Each unicast MAC address is globally unique, and the IEEE manages and assigns such addresses. Each unicast MAC address consists of a 24-bit organizationally unique identifier, OUI, and a 24-bit value that each vendor can assign by itself. PC1 and PC2 are connected to a Layer 2 switch. Initially, the switch's MAC address table is empty. Each row in the MAC address table is an entry. The entry consists of a MAC address, interface name, and VLAN ID. The VLAN ID is not provided here. PC1 attempts to communicate with PC2. PC1 has already used Address Resolution Protocol, ARP, to obtain PC2's MAC address. When PC1 sends data frames, the source address is PC1's own MAC address, and the destination address is PC2's MAC address. In addition, the switch learns the SMAC address of the data frame and creates a MAC entry based on the SMAC address. This entry associates the SMAC address with the inbound port GE001 that receives the frame. The switch searches its MAC address table for the DMAC address of the frame. If no entry in the MAC address table matches the DMAC address, the switch broadcasts the data frame through all ports except for the port that received the data frame. This broadcast is called flooding. All interfaces in the same broadcast domain as the switch receive this data frame. In addition, the switch learns the SMAC address of the data frame and creates a MAC entry based on the SMAC address. In the entry, the SMAC address and inbound port GE001 that receives the frame are associated. PC2 possesses the received data frame, while the other PCs connected to the switch discard the received data frame because they are not the intended destination. PC2 replies to PC1 by forwarding a data frame through the switch. After the switch receives the data frame, it looks for an entry mapped to the DMAC address carried in the frame. It finds that GE001 is the matching port and forwards the frame through GE001. In addition, the switch learns the SMAC address of the data frame and creates an entry associating the SMAC address with GE0024. Next, let's talk about two important concepts, VLAN and trunk. First, let's introduce the technical background. This is an Ethernet switch. It has 24 ports, and each port is connected to a PC. All ports on the switch belong to the same broadcast domain, a logical subnet, by default. Therefore, all PCs connected to the switch belong to the same broadcast domain. The broadcast domain is a logical subnet. More important, if a user in a broadcast domain broadcasts a data frame, all users in the same broadcast domain receive the data frame and consume resources to process it, regardless of whether they want the frame. As the number of users and broadcasts grow, broadcast frames consume an increasingly large amount of resources. In addition to resource waste, if PCs connected to a Layer 2 switch in a network, say within a company, belong to different departments, these PCs must often be isolated or managed by independent network elements, NEs. As a result, network logic units cannot be planned based on service types. VLANs address these management and resource waste issues. Virtual Local Area Network is a communications technology that logically divides a physical LAN into separate logical broadcast domains. Hosts within a VLAN can communicate directly, whereas devices in different VLANs cannot. VLAN limits the size of a broadcast domain, limiting the number of hosts that receive broadcast frames. VLANs can be planned on switches based on various parameters, such as ports. In the preceding figure, VLANs are planned based on interface names. Ports 1 and 2 are assigned to VLAN 10, and ports 23 and 24 to VLAN 20. PCs connected to ports 1 and 2 are added to VLAN 10, and they are within the same LAN and broadcast domain. Once IP addresses on the same network segment are assigned to the PCs, these PCs can communicate with each other. Ports 23 and 24 within VLAN 20 belong to another VLAN and broadcast domain. PCs within VLAN 20 can communicate with each other. Users in different VLANs are isolated if there are no routing devices. A broadcast frame within a VLAN cannot be flooded to another VLAN because the two VLANs are in different broadcast domains. Each VLAN is a broadcast domain and assigned to a specific IP network segment. VLANs can be planned based on service types. Devices in different VLANs cannot communicate with each other at layer 2. VLAN makes network design more flexible and controllable. VLANs are virtual LANs and not limited by devices. They can be flexibly planned based on service types in various scenarios. Since multiple switches share the same VLAN, PCs that are members of the VLAN can be geographically dispersed as long as they are properly connected to the switches. For instance, in the preceding figure, each department is assigned a VLAN for isolation, and the staff of each department are working at different floors. PCs on different floors can be grouped into a single VLAN. Each VLAN is in a broadcast domain, and all devices within a VLAN belong to the same broadcast domain. VLANs are logical subnets, isolated from each other at layer 2. Frames in a VLAN are not broadcast to other VLANs, and devices in a VLAN cannot communicate with devices in other VLANs at layer 2. However, devices in different VLANs can communicate at layer 3. When VLANs are planned on the switch, each port on the switch is added to a VLAN. Any device that connects to the port is automatically added to the VLAN. Each VLAN is a single logical subnet. VLAN techniques are the basic mechanism on layer 2 switches. Switches use 3 types of layer 2 interfaces: access, trunk, and hybrid. Access ports connect to terminals, for example, PCs, servers, and routers. Each access port can only be added to a single VLAN. Such a VLAN is also called the default VLAN of the access port. Once an access port joins a VLAN, a device that connects to this port is automatically added to the VLAN. An access port by default belongs to VLAN 1. VLAN 1 is the default VLAN used on switches of most vendors. An access port only sends untagged frames and receives untagged frames or frames tagged with the default VLAN ID. To carry data of multiple VLANs, a trunk link can be configured. A trunk link connects a switch to another switch or a router. The two devices of the trunk link must use the same trunk protocol, and their ports that form the two ends of the trunk link are called trunk ports. Multiple VLANs can be created on the switch, and each service department is assigned a specific VLAN. Ports on the switches are assigned to VLANs. Be careful when you connect two switches on which VLANs are deployed. The link between the two switches will carry data of multiple VLANs. After a switch sends the data of a VLAN to the other switch along the link, the other switch must determine a correct VLAN before forwarding the data. to ensure that the peer switch identifies the VLAN of each data packet. The local switch tags data frames before forwarding them to the remote switch. Upon receipt of the frames, the remote switch checks the tags and determines the VLANs to which the frames are forwarded. Such a link between the two switches is called a trunk link, and two ports on both ends of the link are trunk ports. The tagging method is called a trunk encapsulation protocol. A well-known public protocol is 802.1q, also called .1q. The public protocol is supported by all switch vendors. The 802.1q protocol adds a .1q field in each original Ethernet frame and redoes the cyclic redundancy check, CRC. In the .1q field, the VLAN ID field identifies the VLAN to which the Ethernet frame belongs. To carry information of multiple VLANs, a trunk link must be configured. Switches on both ends of a trunk link must run the same trunk encapsulation protocol. Huawei devices support only 802.1q. An access port can only be added to a single VLAN. An access port on the switch connects to a PC, a server, or a router. A trunk port can be added to multiple VLANs and transmit data of these VLANs. The trunk port connects a switch to another switch or an Ethernet sub-interface. A hybrid port can also send and receive frames of multiple VLANs. The hybrid port can be configured to add a tag to or remove a tag from frames of a specified VLAN before forwarding them. Each access trunk and hybrid port has a default VLAN ID, which is called a Port Default VLAN ID, PVID. The port adds a PVID to untagged frames it receives. The PVID of access ports is 1. Since each access port can only be added to a single VLAN, the PVID is the ID of VLAN to which the port belongs. The PVID of trunk and hybrid ports is also 1. Both trunk and hybrid ports allow data of multiple VLANs to pass. The ports adds a PVID to each untagged frame they receive. Original Ethernet data frames, also called untagged frames, are data frames encapsulated using Ethernet. For example, data frames sent by PCs or server NICs are Ethernet data frames. 802.1q data frames, also called tags or VLAN tagged data frames, are Ethernet data frames, each with an 802.1q header. Next, let's use ENSP to carry out some experiments on basic VLAN and trunk configurations. We will go over some basic commands used to create VLANs. First, let's create a VLAN on the switch and enter the VLAN view. Configure the port as an access port and add it to a specified VLAN. First, use ENSP to build a basic environment. Add two S5700 switches. Connect each switch to two PCs. Start all devices. Create VLAN 10 and VLAN 20 on the switch. Configure GE001 and GE002 as access ports and add them to VLANs. Create VLAN 10 and VLAN 20. Use the batch parameter to create multiple VLANs at a time. Configure GE001 as an access port and add it to VLAN 10. Configure GE002 as an access port and added to VLAN 20. After completing the preceding configurations, run the display VLAN command on SW1 to view VLAN information. Configure a port as a trunk port. Step 1. Run the interface name command. Step 2. Run the port link type trunk command in the interface view to configure the interface as a trunk port. Initially, the trunk port does not allow traffic or any VLAN to pass. To allow traffic of some VLANs to pass, run the port trunk allow pass VLAN 10, 20, 99 command. This command allows traffic in VLAN 10, VLAN 20, and VLAN 99 to pass. The following configurations are optional. Set a PVID for the trunk port by running the port trunk PVID VLAN 99 command in the interface view. On one hand, when traffic of VLAN 99 passes through the trunk port sends untagged VLAN packets. On the other hand, after receiving untagged frames, the trunk port considers them from VLAN 99. The default PVID is VLAN 1. By default, the trunk port allows only VLAN 1 traffic to pass. To allow data of other VLANs to pass, add their VLAN IDs to the Allow Pass VLAN list. Okay, let's move on to experiment 2. Each of the two switches is connected to two PCs. PC 1 and PC 3 belong to VLAN 10, with addresses 10.1 and 10.2 respectively. PC 2 and PC 4 belong to VLAN 20, with addresses 20.1 and 20.2 respectively. The objective is to allow PC 1 to communicate with PC 3 and PC 2 to communicate with PC 4. Note that PC 1 cannot communicate with PC 2, and PC 3 cannot communicate with PC 4. This is because they belong to different VLANs, and communication between them would require a Layer 3 device. Create VLAN 10 and VLAN 20 on two switches. Add each port connected to a PC to a VLAN as shown in the figure. Configure the SW1-SW2 link as a trunk link so that users within the same VLAN can communicate across switches. Create VLAN 10 and VLAN 20. Configure GE001 as an access port and add it to VLAN 10. Configure GE002 as an access port and add it to VLAN 20. GE0024 is an access port by default. Configure GE0024 as a trunk port and allow data of VLAN 10 and VLAN 20 to pass through it. Create VLAN 10 and VLAN 20. Configure GE001 as an access port and add it to VLAN 10. Configure GE002 as an access port and add it to VLAN 20. Configure GE0024 as a trunk port and allow data of VLAN 10 and VLAN 20 to pass through it. After completing the preceding configurations, verify that PC 1 and PC 3 within VLAN 10 can communicate with each, and PC 2 and PC 4 within VLAN 20 can communicate. The communication behavior is called Layer 2 communications. PCs of different VLANs cannot communicate directly. In the command output, UT:GE001 (U) indicates that the interface is not tagged. The interface is directly connected to a PC. The PCE does not receive tagged packets. TG::GE0024 indicates that packets exchanged between VLAN 10 and VLAN 20 are tagged. configure PC1 to ping PC3 and PC2 to ping PC4. Pings are successful. They can communicate with each other. The receipt of a frame on the switch port refers to when the data frame arrives at the port and enters the switch. The transmission of a frame on the switch port refers to when the switch sends the data frame out through a port. An access port receives and processes packets as follows. 1. If an access port receives an untagged frame, the port accepts it and adds a PVID to it. The PVID is a default VLAN ID, configured using the port default VLAN command. 2. If an access port receives a tagged frame and the received VLAN ID is equal to the PVID, the switch accepts the frame. If the received VLAN ID is different from the PVID, the switch discards the frame. A. The access port is connected to the PC's NIC, and the NIC only possesses untagged packets. B. The access port receives the frame and adds a default VLAN tag. 3. If the VLAN ID matches the PVID, the switch accepts the frame. Otherwise, the switch discards the frame. When the access port sends a frame, the port removes a tag and sends an untagged Ethernet frame. After trunk port receives a frame, it possesses the frame as follows. If a hybrid port receives an untagged data frame, the switch adds a PVID to the frame. If the PVID is in the Allow Pass VLAN list, the switch accepts the frame. Otherwise, the switch discards the frame. The default PVID of the trunk port is 1. VLAN 1 is in the Allow Pass VLAN list by default. After a trunk port receives a frame, it processes the frame as follows. If a trunk port receives a tagged data frame and the received VLAN ID is in the Allow Pass VLAN list, the switch accepts the frame. If the VLAN ID is not in the list, the switch discards the frame. Before a trunk port sends a frame, it processes the frames as follows. If the VLAN ID of a frame received by the trunk port matches the PVID and is in the Allow Pass VLAN list, the switch removes the VLAN tag and forwards the data frame. If the VLAN ID of a frame received by the trunk port does not match the PVID but is in the Allow Pass VLAN list, the switch forwards the data frame without changing the VLAN tag. If a hybrid port receives an untagged data frame, the switch adds a PVID to the frame. If the PVID in the Allow Pass VLAN list, the switch accepts the frame. If the PVID is not in the list, the switch discards the frame. A hybrid port processes a data frame as follows before forwarding it. If the VLAN ID is in the Allow Pass VLAN list, the port forwards the frame. Commands can be used to determine whether GE001 sends a frame with a VLAN tag. The port hybrid untagged VLAN command allows untagged frames to be sent. The port hybrid tagged VLAN command allows tagged frames to be sent.